Hello everyone, I'm presenting our work, Preserving Linear Separability in Continual Learning by Backward Feature Projection. In class incremental continual learning, a model needs to learn over a sequence of tasks, and within each task, the model sees some new classes and learns to classify them. This requires the model to learn some feature directions along which these classes are linearly separable. In continual learning, these features need to be accumulated such that all classes can be classified. But in reality, the continual learning model only focuses on the features that are important for the current task and forgets the old ones. We call this feature forgetting. And in this case, the feature vectors from different classes are not separable anymore, and this leads to catastrophic forgetting. In this work, we aim to preserve the linear separability in continual learning by backward feature projection, or BFP for short. BFP allows the new feature to change up to a learnable transformation of the old ones. We show that BFP preserves the linear stability of the old features while allowing new features to be separated over the previously unused feature subspace. We combined BFP with experience replay baselines and showed that this small change can significantly boost class incremental learning accuracy and reduce forgetting. Now let's dive deeper into the motivation of this paper. Suppose given the training data of continual learning, a classification network is trained to predict the logits. Suppose we break down the model into a feature extractor and a linear classifier, and take a closer look at the learned feature space. We will see that two classes in the first task will be linearly separable along a feature direction, which is the x-axis in this case. In continual learning, this model will be then trained on a second task. Now if we consider the feature distribution of the new task before training on it, we will see that the new data is not separable in the feature space. This is natural because it has not been trained. Then the model is trained on task 2. In an ideal case, we will see that data from both tasks are linearly separable. Now let's take a closer look at the feature space before and after learning task 2. We can see that before training, the model only uses X features to classify the old classes from task 1, and after training, the model picks a new Y feature to classify new classes. We can see that in the forward process, features are stretched along a new dimension to make new classes linearly separable. And in the backward direction, the features can be viewed as being collapsed along a feature dimension. So there should exist a linear transformation that maps the new feature to the old ones. But what if forgetting happens? In this case, the model learns well on the new classes from task 2, but forgets the features learned from task 1. And the classes from task 1 will not be separable anymore. This is feature forgetting, and in this case, there is no linear relationship between the old and the new features. This motivates our method, backward feature projection. It enforces the linear relationship between the new and the old features by learning a linear projection matrix for feature regularization. In this case, it preserves the linear separability of the old features and reduces catastrophic forgetting. Here we formally define our method. Suppose we have an old feature extractor that is the model checkpoint at the end of last task, and a new feature extractor, which is the model that is being continually learned. Their extracted feature vector for input x is z' and z, respectively. Our method uses a linear projector, essentially a matrix of d by d, and the parameters in this matrix are learned by gradient descent. The proposed BFP loss is defined as an L2 regularization between the old features and the transformed version of new features. Similarly, we consider a simpler baseline feature distillation, where we don't have the linear projector, but only the L2 loss between the features. In experiment, we test the BFP with experience replay. The detailed algorithm is shown here. We maintain a memory buffer. Training examples are stored in the memory using reservoir sampling and replayed in the later iterations. For replayed examples, we compute the cross-entropy loss and logits distillation loss inspired by a recent work, DER++. And we additionally apply our proposed BFP loss on the replayed examples. The matrix A is initialized randomly and updated using gradient descent. We evaluated our method on 3 popular but challenging datasets in class incremental learning and report their accuracies over all classes at the end of training. And here come to the results. Compared to the experience replay and the DER++ baseline, the proposed BFP method can boost the performance by significant margins. This is even more obvious when the size of the memory buffer is limited, where we can see an improvement of 6 to 8% in terms of final accuracy. And our method also outperforms other state-of-the-art methods in continual learning. We also compare BFP with a simple feature dissolution baseline, and again we see BFP outperforms. We believe that this is because feature dissolutions puts a harder regularization on the features and limits the plasticity during training. So why does our BFP achieve such good performance? We claim that BFP results in a better feature space where classes remain linearly separable, and we will show this using experiments of linear probing. Specifically, we take the final feature extractor after continual learning and keep it frozen, but we reinitialize the linear classifier. And we take a small portion of training data of all tasks and use it to retrain the linear classifier. The linear probing accuracies will be higher if and only if the feature space is linearly separable among all classes. Here we show the linear probing results on split 0-10, and we can see that compared to the baseline DER++ and feature dissolution, BFP results in a higher linear probing accuracy. We also perform this analysis on a naive fine-tuning baseline. In this setting, there is no memory or replay, and the model is simply trained sequentially on different tasks without revisiting any of the past data. We can see that this naive baseline results in catastrophic forgetting in the feature space, but we can still see a huge performance boost brought by BFP. Also, the linear probing performance is even comparable to the complex experience replay method DER++, and note that fine-tuning with BFP does not keep any training data in continual learning, but still it preserves the linear separable structure of the feature space. In conclusion, we propose backward feature projection, a simple but strong method to reduce forgetting in continual learning. We showed that BFP can reduce feature forgetting by learning a more linearly separable feature space. Experiments showed that BFP can boost continual learning performance by a significant margin, achieving state-of-the-art results. Thank you for listening.